Hi everybody, my name is Timofey and this is a video about my work for Shadowrun Russia LARP. This is the last video in the Maps and Magic series and it is devoted to the code. Here is a little bit of context. This LARP took place last summer. It was about a cyberpunk setting and information space was a big part of the game and models. There were many experimental technical solutions. IT systems are taken from IT report. I will talk about maps and magic, but I'd like to highlight that it was only a small part of the whole IT system. This slide shows links to the previous presentations if you need to refresh the context. This presentation is about technical aspects. I will tell you about the high-level source structure. Then I will talk about the Microengine from idea to implementation. I will tell about problems in the original concept and how they were solved. And in the end, I will tell you about the maps. Starting with sources. Link to the Maps and Magic repo, SR 2020 final branch. Let's open it. README describes project building and running in a demo or development mode with the incremental build. Demo and development. The four main packages are the main server, the main client, the player server, and the player client. Main server implements entities editing, locations, beacons, spirits, mana ocean, and complex actions like game cycle work, external systems communication, and character actions implementation. The main client is the administrator's client. It implements entity editors, data views, and Emicom map. The player server supports the Mage's web application. This server sends location spirits and mana ocean updates to the web application to make magic sound work. The player client is the Mage's web application. It provides the way to work with spirits, catch spirits, scan totems, and run magic sound. This is the high-level components interaction schema. The main server broadcasts data to the player server via server send events. The player server sends requests to the main server via HTTP. The main client works with the main server via WebSocket and HTTP. The player client works with the player server via server send events and HTTP. External systems were connected with PubSub and HTTP. The second part of the main packages. Client core is the core of the main client. It contains generic React entities and maps and magic components. Event Engine is the most important package. It contains types, core use case functions, generic services, and Microengine implementation. Client Event Engine contains Microengine configuration for the main client. Server Event Engine contains Microengine configuration for the main server. This schema shows the main package's dependencies. All packages depend on the Event Engine, but these dependencies are not shown for simplicity. Auxiliary packages. Deploy scripts contain commands for client building. Hacks and fixes is a hacks package. Track analysis is a special web client for positioning system work investigation. It is in non-working condition. Most of the data package is about data for track analysis. Also, this package contains GeoJSON data for Izumrud Recreation Center and initial game area markup from Google Maps. Translations contain Russian and English localization for the main client. Moving forward to Microengine. The idea of a microengine is creating a state manager for storing and updating the state of the application, which has a modular structure and implements an event emitter. The main purpose of the event emitter is detailed state change notification. What did I want from the microengine? It should work both in the browser and on the server. It should support synchronous operations and events for the asynchronous operations. I didn't want to use promises, but later I changed my opinion. Redux inspired me, but I wanted to subscribe to specific data changes. Microengine should work as a computing core, so data inside it changes often. For this reason, I refused the data immutability approach. gameModel is the microengine facade. All users of microengine should work with gameModel. There are three operation classes in gameModel API: get for data retrieving, execute for action execution, and event subscription. gameModel is the service call and events dispatcher. It redirects external calls to the appropriate service. Services are the modules loaded in the gameModel. They implement specific aspects of the gameModel. For example, Spirit Service implements spirit creation and editing, and Spirit Movement Service implements spirit moving by schedule. Each task is solved by some service, and each service has metadata, which data it can provide, which actions it can execute, and which events it can emit. gameModel takes the metadata from the service and uses it for calls routing. It is supposed that there is only one service implementation for each type of request or action. Important point. Services are not web services, and the gameModel is not an HTTP request dispatcher. Services are JavaScript objects which implement their metadata contract by requests, actions, and events. They can return data or execute actions synchronously. Also, they can interact with each other via gameModel. This is a Spirit Service metadata example. We can get data for all spirits or a single one. We can start spirit creation, updating, cloning, or removing. The service itself works as a cache. It is supposed that there is external persistent storage, so service emits something requested for external change. We can start spirit creation, updating, cloning, or removing. The service itself works as a cache. It is supposed that there is external persistent storage, so service emits something requested for external storage. And if the service state changes, it emits spirits changed. Services can interact with other services via gameModel. For example, Spirit Movement service wants to get the current spirit list and the list of routes to update spirit positions. Without this data, it can't do its job. And we want to be sure that this data exists in the model. First, we extend the service metadata with the model requirements. This is an enumeration of service requirements. Second, after initialization, gameModel does a consistency check and throws an error if some service requirements are not satisfied. A shallow consistency check was implemented in the very first JavaScript implementation. Later, the code was moved to TypeScript, and metadata was transformed into typed service contracts. Example of external requirements. The same Spirit service expects confirmation events from external Spirit stores, like PostSpirit confirmed and PutSpirit confirmed and other, and setSpirits event for full Spirits reloading case. Next question, what about external data? gameModel provides an interface to use the data inside the gameModel. But where did the data come from? First, prototypes use local storage, but external systems need better abstraction. This abstraction was named data bindings. Data binding is an object which encapsulates work with some external data source and transforms all operations in gameModel events. For example, one data binding implements CRUD operations for the spirits and other wraps PubSub subscription. Data bindings are independent of the game model. For this reason, Event Engine, top-level object, manages game model and data bindings interaction. This is how it works. There is an Event Engine that contains data bindings and game model. There are many services inside gameModel. Data bindings are external system adapters. Data bindings interact with gameModel via events. gameModel provides requests, actions, and events to user code. I will show the process of new service creation. Suppose we already have the server and the client. The server has gameModel with ManaOcean service. ManaOcean service implements the ManaOcean game cycle. It recalculates the mana level in all locations one time per minute. We need a switch in the client that turns on and turns off the ManaOcean game cycle. We need it for spell cast checking. First, we create a new service in the server, ManaOcean enable service. It will store the Boolean variable enable ManaOcean and provide a getter and setter for this variable. This is a simplified example. Service, variable, getter, setter, and service metadata. Add ManaOcean enable service to the gameModel. To use enable ManaOcean, we need to add a getter call to ManaOcean service metadata and call it in the relevant place. Next is client changes. The client should use the same ManaOcean enable service as in the server. Creating gameModel with ManaOcean enable service in the client. In the next slides, I will show how the state update process should work with several microengines. First, consider the state update process in React. We have a simple controlled input in React. To change the flag, user should click on the input. Click handler calls setFlag function. State changes and input gets a new value. The same operation with gameModel. First difference, flag is received via props. Skip this for now. In other aspects, it works like in React. Click, updating gameModel state, updating checkbox. Now add the server gameModel. In this case, state update goes in 5 steps. Click, client state update, server request, server confirmation, updating checkbox. Sequential state update between models is named state update chain. We need to synchronize server and client states. It requires 3 operations: initialize state, get change state from the server, modify both local state and the server state. All these cases should work via events. We have identical services both in the server and the client, but the services themselves should not know about it. Service must be ready to be in the state update chain. Service should emit event something requested. On set enable mana ocean, call for it. Next, service waits for event something confirmed. On receiving it, changes the local state and emits something changed event. This is an example. Also, it is possible to change the local state in the setter, this function. Something must transform something requested event in something confirmed event. In the simplest case, redirect service does it. This is just event type switcher. State update chain in the sequence diagram. User clicks, then client's mana ocean enable service sends requested event. The message is sent via WebSocket, and redirect service transforms requested to confirmed. Server's mana ocean enable service receives confirmed event, updates the state, and emits enable mana ocean changed. WebSocket wrapper listens to this event and sends it to the client. Client's WebSocket wrapper transforms changed event to confirmed. The final schema adds WebSocket wrapper and redirect service. The client states are updated in all connected clients. Service and wrapper. We solve the problem. Good news, the service code is identical and reused both in the server and in the client. Service works via events with all their pros and cons. Bad news, WebSocket wrapper is a smart object which has a set of rules for event transformation. In the real game, it contains 18 transformation rules, so it was very big. Moving forward to the problems of the initial concepts and following changes. Initial gameModel public API supports only requests and actions. In many cases, the action was a wrapper for event emitting from the service. To avoid this problem, I added event emitting to the gameModel public API and removed extra code from the services. Before, set enable mana ocean, action call, and event emitting. This one. After, just event emitting. When code moved to TypeScript, I introduce service contracts. These contracts include types and data for all service requests, actions, and events. Data bindings also get such contracts, but only for events. It raises two questions. First, if a user can emit an event for data binding by passing the service, then maybe data binding is the service itself. Second, data binding's events should be checked in gameModel consistency validation. If it was a service, then it just works without additional validation changes. Plan for the future uses only services and no data bindings. There are three microengines in the Maps and Magic system. The main server microengine uses 27 services and 17 data bindings. The layer server microengine uses 11 services, from which 8 services were reused. The main client microengine uses 17 services, from which 14 services were reused. Service reuse helps a lot during the player server development. Services are the kind of code decomposition technique that simplifies testing and reusing. I didn't write tests, but I plan to do it in the future. An interesting idea is that with Microengine it is possible to do both unit and integration tests. It will be easy to make custom microengines for 1, 2, 3 or other services and check service interaction. And one more opportunity. If we use the same services, then it is possible to run the server engine in the client to simplify the development process. There are some problems left in Microengine design. First of all, lack of typing. There is no way to get the list of applicable requests and others from the specific gameModel in TypeScript. The same is related to the service consistency check. It is not validated by TypeScript. Second, are improvements in the client-server model, which includes simplifying logic in WebSocket wrapper and promise support. Now about maps. I worked with maps for Shadowrun to get the maps programming experience. I use the Leaflet library and integrate it with React. I made about 10 maps and 25 layers, so I get my experience. This is my final component structure. The map is the top component. It wraps the leaflet map and provides an event emitter for map interaction. Each layer component controls one or a few leaflet groups and updates them on data change. Data hooks are data providers for the specific layer components. To simplify layer components logic, I made a very simplified version of React reconciler. Function getRdiff takes arrays, key extraction function, and comparator. On output, it returns list of added, removed, and changed objects. This is an example of the map component, an Imicom map. The main component is the map which gets gameModel and passes it to all layer components. Next, there are 4 basis layer components: satellite map, isomroot contour, building plans, and non-editable geolocations. Next, there are 3 special layer components. First, draws character in clinical death markers. The second draws the table of characters' death with information. Third triggers sound signal on receiving clinical death information. If we look at the rescue service layer export, we will see data hog with data for a rescue service layer. It collects necessary data from gameModel and passes it to the component via properties. Map summary. There are a couple of known problems, but they are not critical. It was easy to work with maps. The Leaflet is an excellent library, so I want to use it further. The next sources contain more LARP information. If you have any questions, please ask them in video comments. Wish you good games! Thank you for your attention.